Okay, I think we can start. So welcome everybody to the second week of the school. And the speaker of today is Cécile Repellin from the CNRS, and she's going to talk about interaction-driven insulators in flatband moire superlattices. So Cécile, whenever you want.
Okay, thanks, Maya. Well, first of all, thank you very much for the invitation. I'm very happy to be here. Of course, I'll join everybody in saying that it's super sad that we should be in San Sebastian, but we aren't, at least for most of us. So yeah, I hope to see a lot of you in person soon. So hi, everyone. So today I'd like to talk about insulators in moire superlattices. So as you know, moire materials have become this incredibly versatile platform. And I think one of the things that's super exciting is that we can realize a lot of quantum phases in moire materials in general. And I think Pablo last week talked about many of these phases. Some of them are correlated insulators. Of course, there was also superconductivity at the beginning of this boom of twisted bilayer graphene and other moire materials. But since then, ferromagnetism has been observed, quantum anomalous Hall effect, as well as other phenomena such as nematicity, ferroelectricity, and strange metals. So for today and for this whole series of lecture, I would like to focus on a few of them. So correlated insulators will be at the center of these lectures, and that will include phenomena such as ferromagnetism and the quantum anomalous Hall effect. So a mix of topology, interactions, all of that to see how these interesting insulators can arise in moire materials. So this is the rough outline of the lectures. Today I'll start with a quite progressive introduction on incompressible phases and their filling fractions, and especially those insulating phases that can be found in moire materials that maybe couldn't completely be observed in other types of solids. So this part will be a little bit phenomenological with a little bit of experimental data and quite general, I would say, very, very non-technical. Then I will focus on one specific moire material, which is magic angle twisted bilayer graphene, aligned with its hexagonal boron nitride substrate. And I will distinguish different cases. So for today, we'll only look at integer fillings, and we'll be interested in ferromagnetism and quantized anomalous Hall effect. So the idea is to understand this phenomena from the microscopic point of view. And then later on, so today and tomorrow, we'll move on to fractional fillings and other types of phenomena, such as the fractional quantum Hall effect or symmetry breaking phases. So phases that basically require a fractional filling of the mini bands in twisted bilayer graphene or other moire materials. And finally, if time allows, I'd like to get a little bit more technical with some, by explaining a few numerical signatures of fractional quantum Hall phases, since fractional quantum Hall phases will be the focus on the second lecture. I like to show you some methods of, how do you diagnose those phases when you're doing numerics, and you want to know whether you have a ground state that has topological order or not. But yeah, so for today, we'll focus on integer filling for the most part. And as I said, I'm starting with a very progressive overview of incompressible phases. and their filling fraction. So this will kind of serve as a something very general that allows me to give a framework to all of my lectures. We're starting with the very basics, which are band insulators. So those are the simplest insulators you could think of. I said we were going to talk about filling fraction a little bit. So here what I mean is that in a band insulator, you have a very simple relationship between the number of electrons and E and the number of unit cells. So here we are on the lattice, there's no magnetic field. And band insulators arise when you have a proportionality between the number of electrons and the number of lattice unit cells. And if you have an extra degree of freedom, like typically you have spin, you'll have bands that are twice degenerate. So you expect band insulators quite simply for an integer which is even. There's a slightly more complicated situation of having an odd filling. So here, depending on the microscopics, you might or might not get an insulator. And if you get one, it can be because spin is polarized, for example, and I will give you a correlated insulator. Now, the next very simple example of an insulator is the quantum Hall effect. And like Jen Cano emphasized in her lectures, in her first lecture, I think, we have a different type of insulator. It's a topological insulator. And here we have also a different relationship. We have the number of electrons now is not tied to number of lattice unit cells, because essentially we are in the continuum. But it's related to the number of flux quanta that go through the system. And here we will find a band insulator in a sense. So we'll have an integer quantum Hall effect as soon as the number of electrons is an integer times the number of flux quanta. So here, I've called this T here, but very often you would call this nu. This is the filling fraction of Landau levels in the quantum Hall effect. And again, you have the degeneracy of spin, even though it's slightly lifted because of the Zeeman effect. So for even integers, you know, the gap is just the cyclotron gap. And for odd integers, well, this is, you also have to include interactions to understand the nature of the gap, but we'll come back to that later. For now, we just need to know that at filling 1, for example, of the lowest Landau level, we have a spin polarized integer quantum Hall effect system. Let's talk a little bit about observables, still in the context of the quantum Hall effect. So when you have an incompressible phase, Streda's formula tells you that the whole conductivity in the right units is given by the derivative of the electronic density with respect to the magnetic field. So d rho dB, which I can also write with my notations, d and E number of electrons, d and phi number of flux quanta. So automatically I see from this relationship that I have a quantized Hall conductivity, which is what defines the quantum Hall effect. And so this is an observable, and that's, you know, this corresponds to the Hall plateaus, the very characteristic signature of the quantum Hall effect. You look at the transverse conductivity, the Hall conductivity, and you see that it evolves as these plateaus, an integer times E squared over H, the quantum of conductance. There's another way to look at the Hall conductivity, which is actually from the longitudinal transports, not the transverse transports. And that could be by looking at Landau-Fan diagrams, such as this one. And the idea here is really to use Streda's formula to extract the Hall conductivity. So here, what I'm showing is the longitudinal conductance for different colors. So blue means very small conductivity. So it means you have an incompressible phase. So every time you have an incompressible phase, you can use Strela's formula. And that will give you these lines in the magnetic field versus density plane. And from the slope of these lines, using Strela's formula, you can recover the whole conductivity, which again helps you recover, helps you realize that you do indeed have the quantized value for the whole conductivity. Now I've worked in two very different regimes. First, I had a band insulator with no magnetic field, and then I had a system with a strong magnetic field, and I had two different relationships for NE versus number of unit cells, or NE versus number of flux quanta, but I can very well put them together and generically observe incompressible phases when NE is the sum of S and S, and T and phi. Again, if I remove the magnetic field, I find the first relationship. On the other hand, if I'm in the quantum Hall regime, which is mostly continuum, the first part is negligible compared to the second term. To show that this approximation was indeed justified in the quantum Hall regime, I can just compute the typical value of the magnetic length for a typical magnetic field. Let's say 10 Tesla, which is already a very decent field. Then the magnetic length will be equals to 8 nanometer, which is much, much larger than the lattice constant for a typical lattice. For example, if you take the graphene, if you take single layer graphene, and you wanted to have one flux quantum in every hexagon, you'd need a magnetic field of around 40,000 Tesla to reach this sort of order of magnitude, which is completely crazy and unfeasible, of course. And now, of course, you know where I'm getting at, which is, to me, maybe the first advantage, or the first things that makes moire systems very interesting, is to change the length scale. So by working with moire superlattices, a length of around 10 nanometer is something that is very doable. Now you can indeed have a lattice, superlattice actually, with a lattice constant that is of this order of magnitude. So you can have the order of magnitude of the magnetic length roughly equal to the lattice constant. So here I'm showing some, again, some experimental data where this phenomenon was observed and explored. So the data here comes from graphene aligned with a substrate of hexagonal boron nitride. And so both graphene and HBN are hexagonal, and they have almost the same lattice constant, but not quite. There's a very small 1.8% mismatch between the two lattice constants. And when you align those two lattices, this creates the moire superlattice with the largest possible unit cell. And it will be around, or maybe a little bit more than 10 nanometers. So that will allow you to explore new things compared to your purely quantum Hall regime, and more specifically, it will allow you to explore the regime S non-zero in this Diophantine equation here. So if I'm looking a little bit closer at the data, so again, this is longitudinal conductance. So basically, I want to look at all the very at the darker colors here, which corresponds to smaller longitudinal conductance, because that means I have an incompressible phase, and I will see lines in that case in the B versus electronic density plane. So here, the unit is the gate tension, which is what allows you to actually change that density in the sample. So I have here my usual Landau levels, let's say, all the basically those lines that that go through, that cross the y-axis at 0 field. This is just the typical common Hall effect, but you see, for example, around here or around there, that there are other lines, for example, this one or that one, that correspond to a non-zero S. So you really explore this, you start exploring the full possibilities of the combination of lattice and magnetic field. And I didn't say it, but you've probably noticed that there were other lines that didn't have a linear slope. They have a fractional slope, and I haven't. So these correspond to fractional quantum Hall states. I haven't talked about this yet, but I'll come to that later. So exploring all those possibilities means that you're exploring the Hofstadter butterfly that probably you know or have heard about. So basically, the idea is that when you have a magnetic field on the lattice, you can explore that with a tight binding model by doing a Pyle substitution, meaning that you'll take into account the effects of the magnetic field by replacing those simple Hoping terms by a Hoping terms times a phase. And the phase is given by the integral of the vector potential along that path taken for the Hoping. So this is what Hofstadter realized is that then you could write on a model like this, and well, you can write it down in any lattice. The simplest is the square lattice, but you can do a triangular or honeycomb and so on. And that will, if you solve the Hamiltonian in that case, or the Harper's equation, this will give you a spectrum which has a self-similar structure. It is fractal. And each gap within the spectrum, so the way to look at this is to fix phi, the flux quantum, and this is the y-axis corresponds to the energy. Each gap corresponds to an incompressible phase. So if you are at small flux, you'll recover your typical Landau levels, but as you go more towards the phi equals to phi naught, the unit of flux quantum, well, then you have a very different physics. So this is the first point that I wanted to emphasize for this first lecture, is that, well, moire superlattices, they allow you to first explore the Hofstadter butterfly in the regime phi close to phi naught or half phi naught. So they allow you to really go into this very interesting physics, which combines lattices and magnetic fields. And finally, so this is moving on to a different aspect. You can consider fractional fillings and fractional conductivity. So here I'm continuing my overview of incompressible phases, if you like. So again, using that Diophantine equation, instead of having S and T be integers, I can have rational fractions. And okay, maybe I should be very clear about this. I'm not saying that there's an insulator for every S and T integer or fraction. I'm saying that there can be one. That doesn't have to be. That will depend on the microscopics of the system. Okay, so what's quite cool is you can, again, thanks to this enlarged unit cell, allowed by moire superlattices, you can explore all different types of combinations of S and T being non-zero and also being fractional or integer. So here I am showing you some data that comes from Andrea Young's lab. And here it is a bilayer, Bernal stacked bilayer graphene aligned with the substrate of hexagonal boron nitride. So the origin of the moire superlattice is, again, like the previous data I showed, is again due to the lattice constant mismatch between graphene and HBN. And again, this is data in the B magnetic field versus electronic density plane. Here, this is not actually conductance data, but capacitance. This is a different way of probing whether your system is compressible or not. But again, you have these different lines, which have been analyzed by the authors in this second diagram here. And they can identify a lot of different combinations of S and T being zero, non-zero, fractional, or integer. So if S is, yes, so T, again, according to the Strata formula, as soon as you have an incompressible phase, T basically gives you the whole conductivity. So if T is fractional, T equals to P over Q, then you have a fractional conductivity. And then if S is zero, basically no lattice effect, no superlattice effect, we call that just fractional quantum Hall effect. But if it's non-zero, that means that you've obtained your you obtain your fractional quantum Hall effect by filling a Chan 1 band that comes from the superlattice, and we'll call that a fractional Chan insulator, because this is, there's no way to explain the phenomenon without the reasoning including the superlattice. Another option is to have a fractional filling. And in that case, you don't necessarily have a fractional conductivity. You could also have a symmetry broken phase that has an integer conductivity. So that corresponds to the pink line in this diagram that the authors have called symmetry broken Chan insulators. So you still have probably a non-zero Hall conductivity. T is non-zero, but not fractional, and a fractional filling. So you can, well, the insulator then comes from breaking a spatial symmetry by forming a charge density wave. But I'll talk more about this in the second lecture. Okay, so that's pretty much all I wanted to say for my overview. I think I've talked about a few different phases, all insulating, and all fit within that framework of having a number of electrons that's equal to S times the number of unit cell and plus T times the number of flux quanta. And the first message that I've emphasized in that overview is that length scale matters here, and moire superlattices allow you to have a lattice constant that is of the same order of magnitude as that of the magnetic field. So that's the first thing, and it's already super important and really new to be able to to explore all the aspects of this Hofstadter butterfly physics. But as we now know since a few years, it also allows you to do many other things. Moire can allow you to do many other things. One of them is to have topology without any magnetic field. So I think this is a theme that was explored quite a bit in Andrei Bernevik's lectures. And here I will be mostly interested in the case where you can have a non-zero Chan number, but there are other things such as fragile topology. And finally, moire systems allow you to have flat bands thanks to magic angles, for example. So it allows you to explore strong correlations. So now I am moving on, and instead of exploring this first aspect, I'll be exploring the interplay of this topology and flat bands physics. And I'm going to do it by focusing on one particular moire system, which is magic angle twisted barrier graphene aligned with hexagonal boron nitride. So I'll be talking first about band properties. So for this part, there's going to be a bit of overlap with Andre and Oscar's lectures from last week, but this will be quite short, and I will quickly go through things that are new in principle compared to these lectures. So right now, I'm setting this in the context of band properties, so I'm only considering single particle properties for the time being. Okay, so twisted barrier graphene. So I think by now you've probably heard this many times, but let me go through it one more time quickly. So in monolayer graphene, you have a hexagonal lattice with A and B sublattices. And if you diagonalize the Hamiltonian, you will obtain this structure where you have Dirac cones at every corner of the Brillouin zone. And you have two inequivalent corners, which are called valleys, K and K prime. You also have two spins, so that will give you a four-fold degeneracy. Now, twisted barrier graphene consists in stacking two layers of graphene on top of one another and having a controlled angular mismatch between those two layers. That means that I have, in real space, a much larger lattice constant, and in momentum space, a much smaller Brillouin zone. I can, so if I'm focusing on that, I can see that when the angle theta, the rotation angle theta is small, the two K prime coming from top and bottom layer are next to one another. They will form one mini band. Well, more than one, but they will form one mini Brillouin zone, let's say. And then the two K coming from top and bottom layers will form the other mini Brillouin zone. And there's no, well, the scattering between K and K prime valleys is exponentially suppressed. So we can neglect it and consider the two valleys independently. Now, you know, as you have your superlattice potential, that means that you are folding all these, well, you are folding the original bands of graphene several times. So that will create thousands of mini bands. And of those bands, we want to focus on the conduction and valence bands. So thanks to the scattering between, well, thanks to the tunneling between the top and bottom layers, there are gaps that are opened, and conduction and valence bands are separated by a gap from lower and higher bands. So you know the usual story that as you go to very small angle, there's a, well, you flatten the band very much until you reach a magic angle of around 1.1 degree. And then if you keep going down, they will, well, the bandwidth will start growing again, start increasing again. So, so you will stop at the first magic angle. And okay, so this is now where the story now differs slightly from the regular magic angle twisted barrier graphene, is that we're going to consider the magic angle twisted barrier graphene in the case where it is aligned with its hexagonal boron nitride substrate. So now I'm going to slow down again to treat this part. So let me describe the model that we are using to describe the situation. So as is the case for magic angle twisted barrier graphene, we neglect spin-orbit coupling. It's extremely small. Intervalley coupling is also neglected in this model because it's exponentially suppressed. And what we'll do is we start from the Bistreser-McDonald model. Again, this is just a reminder from what you did last week. So we can separate valley K plus and valley K minus, however you want to call them, but the valleys corresponding to, well, valley plus correspond to one chirality, and valley K minus is the time reversal partner of that valley. So we can write down the Bistritzer-McDonald model in this valley, in this one valley. So here I'm writing it down in K space, and we have spinors here in corresponding to the top and bottom layers, and each of these psi is itself a spinor in sublattice space. So it has two components, an A component and B component. So if really I wanted to expand everything, I would have a 4 spinor here. And so here we see, so this is just a reminder of the fact that we have Dirac cones. Well, we have the Dirac particles for both the top and bottom layer, and the chirality for the top and bottom layers are the same. So this is the diagonal part of the Hamiltonian. We have sigma matrices, Pauli matrices acting in the sublattice space here. And we have the second part, which is the moire scattering or the coupling between the two layers, if you prefer. And this coupling occurs for wave vectors that are reciprocal lattice vectors of the moire superlattice. So they are called GJ in this case, in this language. And TJs are terms that I'm not going to repeat here what they are. This was quite well described in both Andre's and Oscar's first lectures last week. Okay, so this is just and I didn't mention the fact that so you could add, typically since we have rotated layers, it would make sense to add a rotation for to rotate one of these Dirac dispersions. You can in fact neglect it again, as was explained last week. Now to this plain Bistritzer-McDonald model, I'm going to add a term which breaks C2T symmetry. And that terms come from the alignment with the hexagonal boron nitride substrates. It's maybe it gets a bit confusing here because I already talked about aligning graphene with an hexagonal boron nitride substrate earlier, and the effect I talked about was to create a moire superlattice. Now I'm talking about creating a mass term. So both of these effects exist, and depending on the context, they might be, more or less important. This is, I want to focus on that aspect, the fact that you are breaking C2T symmetry. So this is just due to the fact that boron nitride, well, this is it has two types of atoms, so it will just act differently on A and B sides when it's well aligned. Twisted bilayer graphene, similarly to single layer graphene, actually, its Dirac cones are protected by this C2T symmetry. So by breaking the sublattice symmetry, you break the C2Z symmetry, which in terms, in the end, breaks this product of symmetries. So effectively, this is like adding this sigma Z term in the Hamiltonian. And note that I've only added it to one layer and not to the other, because typically only one of the graphene layers is aligned with the substrate for practical reasons. But this is enough to open a gap in all of the Dirac cones. Yeah, so this the amplitude of this gap is around 15 of this mass is around 15 milli-electron volts, and this is a gap that was experimentally observed in these experiments, and later analyzed theoretically. This is a little bit subtle because in principle, since the two lattice constants, the one of HBN and the one of graphene, are not exactly the same, you should basically add a plus delta AB sigma Z on one zone of the superlattice, and then half a paired further, you should have a minus delta AB sigma Z. But it turns out that effectively, this is not what happens. Effectively, it's enough to just add this one uniform term on the whole lattice. All right. So you've opened this gap. So you started from these this condition and valence band that were touching each other through Dirac cones. You've added this mass term in one of the graphene layers, which has opened a gap thanks to breaking sublattice symmetry. Now this means, because you have a gap, you have a well-defined Chen number in each of the bands. Yes?
Cécile, you have a question from
Sure.
Martin Gutierrez. This also breaks the particle hole symmetry that was conserved by rotating the sigmas.
Yes. For me, it doesn't really matter that particle hole symmetry is not conserved. So yes, it's broken.
Okay, thanks.
All right. Yeah, so you have now a well-defined Chen number for each of these bands. And because you started from a model where in a given valley, you had the same chirality for each Dirac node, adding this mass will actually create a non-zero Chen number in each of the bands. So, this is summarized in this picture where if you focus on valley minus, for example, you may have a Chen 1 conduction band and a Chen -1 valence band. That's identical for both spins. And in valley plus, the conduction band, on the other hand, will be -1, and the valence band will be 1, in accordance with the fact that valley minus and valley plus are time reversal partners of one another. So if I focus just on the conduction band, schematically, I have these 4 bands that are almost flat because I'm at magic angle, and that have these different Chen numbers depending on the valley, and additionally I have that spin degeneracy. Okay, so this was the overview of the band structure properties of magic angle twisted barrier graphene aligned with hexagonal boron nitride. Now I'm adding another element, which is interactions. And this is where we start observing emergent ferromagnetism, as I'll explain now. So let me start with a few experimental facts. Magic angle twisted bilayer graphene aligned with HBN has been realized before, and this is what is seen in various experiments. So first of all, there's a hysteresis of the whole conductivity of magnetotransport in general. And this hysteresis indicates an emergent orbital magnetism. So this data is from David Goldhaber-Gordon's group, and this was the first time that this hysteresis, this emergent orbital magnetism was found, and it was found for filling 3, meaning that in mean field this would correspond to in the conduction band filling those 3 bands out of 4. And subsequently, a quantized anomalous Hall effect was also found. So note here that in the first experiment, the whole resistivity is quite large, 6 kilo-ohm, but that's still smaller than the Frank-Litting constant, which is about 5 times larger, a little less than that. So subsequently, quantized anomalous Hall effect was also observed. So here again, there's a hysteresis of the Hall resistivity. And maybe I should explain that the hysteresis comes from the fact that as you increase magnetic field, if you have a very large magnetic field in one direction, you're going to fully polarize your system because the magnetic field couples to the Berry curvature basically in your system. And that's going to value polarize the system entirely. And as you decrease the magnetic field going that way, you stay on the plateau of Hall conductivity because you remain in that polarized state, and you're even at you're still quantized at 0 field. So you do indeed have a quantized anomalous Hall effect. There's no more magnetic field. It's a spontaneous polarization, spontaneous time reversal symmetry breaking. And as you go down to very negative field, or you invert the polarization, like in a magnet. Yeah, it's probably important to specify the fact that previously quantized anomalous Hall effect had been observed, but in a very different setting. So this is an observation that dates back to, I think, around 2013 or so. And then the material was very different. What they did is they took some thin films of topological insulators. So the topology was coming from spin orbit coupling in those materials, and then they doped them with transition metals, so impurities that explicitly break time reversal symmetry. Here, here the origin of the time reversal symmetry breaking is very different. There's no doping. It's spontaneous, and it's a material with only only carbon and Vn atoms. So let's, after this phenomenology, let's go into some microscopics. So this is a phenomenon that's often called flatband ferromagnetism, and it can be linked to Hund's rule in atomic physics. So Hund's rule tells you that when you have atomic orbitals that are degenerate, it's energetically more favorable to fully fill one level with electrons of the same spin rather than having electrons with opposite spins. So here it's basically the solid state equivalent of this rule that is observed in magic angle twisted by heliographene, and which shows up through a valiant spin polarization at integer band filling. Well, at least that's what you expect from Hund's rule. And to explore the physical arguments, we can start by thinking of a trivial band, which is not the case here, but there are other twisted or other moire materials where this happens, where the band is trivial. So it doesn't fully require the topology in the form of a Chern number. So if you have a trivial band, then you can write down a lattice model through some 1A orbitals that are exponentially localized, and that could just correspond to that one band. Then you can project the Coulomb interaction onto this band, and that will give you, you will get among the different terms that you'll get a, let's say, Hubbard-U interaction. So you'll get a repulsion between electrons that doesn't depend on spin, but you'll also get an exchange integral, which favors the maximally polarized states. Yeah, so maybe I should also say that this is something that comes from the fact that the overall wave function has to be antisymmetric. So maybe you can think about it if you just have two sides. You can think about it in terms of minimizing the Coulomb interaction. To do that, it makes sense to have wave functions that are antisymmetric in their spatial parts, and to keep the antisymmetry of the overall wave function, then the spin part must be symmetric, so ferromagnetic. But away from that context of the trivial band, you can also think of the case of Landau level ferromagnetism. So this is what I was mentioning in the very beginning of the lecture. When you have Landau levels, you have a spin degree of freedom. And if you consider the case with a filling fraction 1, you completely feel the lowest Landau level, but just corresponding to just one spin. Since you have a Zeeman effect, you could naively think that the fact that you have an insulator in this case, the gap comes from this Zeeman effect, but it's really not the case because the Zeeman effect is very small in energy. So maybe around 0.3 times the magnetic field in Kelvin. Whereas if you consider the effect of exchange in this system, which is roughly of the order of magnitude of the Coulomb interaction, so that's why I'm calculating E square over epsilon LB here, it's going to be of order around 5 times square root of B, also in Kelvin. So for the magnetic fields that are accessible, this second exchange term is always much larger and is really what sets the value of the transport gap in the integer quantum Hall effect with an odd filling. All right. Good. So these were, okay, so I've given some physical sort of intuitive arguments why you should find ferromagnetism in the flat band limit when you have an integer filling. So these are extremely generic. They don't depend on, there's not really anything moire about this except for the fact that you have a very flat band. So that's what allows you to have strong interactions and to have a flat band. I'm going to stay very generic here, but give some slightly more analytic arguments for ferromagnetism. And that requires me to project the Hamiltonian onto the active band. So here, let's say the conduction bands. For this approximation to be valid, you would need the bandwidth to be much smaller than the typical interaction strengths, and which itself should be much smaller than the gap, both below and above the conduction band. It's not necessarily the case, and rather probably not the case in twisted bibliography, but let me still go through the argument because it's interesting, and then we can check how robust it is later on. So here I've written down the projected Hamiltonian. It's we're doing a projection onto a turn band, so it's much easier to do it in momentum space. So V of Q is, well, it's your favorite interaction, and typically you would need you would use a Coulomb interaction, and probably maybe you can take into account the effect of screening in it. But okay, so here this is very generic as long as it is a repulsive interaction. Then rho Q with a little tilde. So the little tilde means that we have done the projection onto the conduction band. And this is something we see here through this form factor, which appears here as the overlap between two wave functions. So I'm showing here the projected density operator for just one Wally and one spin. This is what the tau here means. And so in this form, this is where, well, basically all the, well, the topology and the Berry curvature and all these sort of things, that's where it's hiding when you do the projection. The overall projected density operator corresponds to the sum of all spin and valleys. So yeah, so an argument why there should be ferromagnetism at integer filling in the Flatband limit. So the first very important point is that the projected Hamiltonian is positive semi-definite. And you can see it if you realize that rho of minus Q is actually equal to rho Q dagger. So when you do an operator times this operator dagger, this is positive semi-definite. V of Q is positive because we have a repulsive interaction. So this is a sum, H is a sum of positive semi-definite operators, meaning that all the eigenvalues, the whole spectrum of H is going to be positive or zero. The second argument is that if you take a fully polarized wave function at integer filling, so let's say I'm using filling 3, like in the experiments, then this wave function satisfies, you know, if you rho Q psi polarized equal to 0. If you apply the density, the projected density operator onto it, it'll be 0, which means that psi is an eigenstate of this Hamiltonian with eigenvalue 0. So it has to be a ground state. So it doesn't have to be the only ground state, but it is a ground state. Okay, and I'm now running out of time. Let me just mention what happens if you go beyond the exact Flatband limit and allow a little bit of bandwidth to be non-zero. So now you know you need to go to a numerical approach. You can do Hartree-Fock. And basically, you will walk within the variational space of Slater determinant wave functions, and that will, you know, show you that the fully polarized wave function is the ground state up until some non-zero finite bandwidth. And if you want to go beyond that approach, you can do exact normalization. And add a little bit of dispersion, either something realistic or here I wrote down something very artificial for the dispersion, but I think the idea is just that you have an interaction term, which is Coulomb interaction projected onto the conduction band, and you add just a kinetic energy term, and you see, you just check whether the fully spin and valley polarized states is the ground state of the system or not. And you know, doing that, you obtain that there's a So here, this is a kind of generic result with a lot of different moire systems. But if you look at twisted bilayer in a line with hexagonal boron nitride, it's the purple curve. So you get about 15 to 20% of U for the bandwidth before you do not have a fully polarized insulator anymore. Okay, so I think I'm running out of time. So I will stop here with all the consideration on integer filling insulators in the moire superlattices. Tomorrow and the next day we'll consider fractional quantum Hall state. I'm happy to go back and give more details about the integer filling case if there are questions. I'm happy to talk about them tomorrow or to answer questions now.
Okay. Thank you, Cécile, for this very nice talk. Are there any questions? I have a question myself. If you use Hartree fog to solve the bands of a moire lattice, the exchange potential is the same as in a non-moire lattice?
Well, no, I mean, I'm really not a specialist of that, but I would assume it really, the exchange depends on the whole band structure, right? So, so I think that would be quite different.
Okay. There are two questions. Okay, from Mikel Garcia, is the interaction really much stronger than the bandwidth in TBG, or are they in the same order?
Yeah, I mean, in principle, I think they are of the same order of magnitude. So yeah, it's very reasonable to question that assumption that we're in the flat band limit. But I think that's exactly why we do numerics, is that so that we can check the effect of a small bandwidth. So maybe here it's also maybe why we do observe some correlated insulators at some fillings and not other integer fillings. For example, in this case, I think for MATBG aligned with HBN, I think there's only this churn insulator is only observed at filling 3 and not at filling 1, for example. So there could be, there are lots of macroscopic ingredients, including the bandwidths that can change sample to sample and even within the same sample from one filling to another. So, it could be an explanation.
Okay, from an anonymous attendee, where is the ferromagnetism localized in the TBG?
Where is it localized? I'm not sure I completely understand. So the idea is that you have it's a valley polarization, basically. So so the system, within, maybe it's this, I can show you this picture again. It's this mean field picture where you have a conduction band that's essentially a narrow band with a fourfold degree of freedom for spin and valley. And
the same person says in real space, sorry.
In real space. I mean, are you asking about the...
I guess he asked or she asked about the atomic site, for example.
I think I can answer some of this in the next talk.
Okay. Well, then maybe this is probably better that I'll let you.
Okay. No, there is one last question. In this projected model you gave, comma, you only consider intraband pairing, right? But with a flat band and approximate particle hole symmetry, you could also pair particles of different bands. Given that the gap is small, could you?
Okay, I'm not sure I
You
was
can
able
read
to
it.
follow. Can I read it somewhere?
Yeah, it's in the
Okay,
question and
yes.
answer.
Intraband pairing, yes. Yes. Yeah, so there is, so is that like, basically, I guess that's a question about projecting the interaction onto the active bands. And I mean, there's an effect from the remote bands, which will renormalize the bandwidths. That's for sure. I don't know if it's the question. Yeah. So yeah, I think that's what I can say here. Maybe I should emphasize that this approach doesn't really try to be super realistic in terms of taking into account all the effects and the interaction with other bands and so on, but rather try to ask in a generic way. We know that interaction with higher bands is going to renormalize the bandwidth. So, no matter where that bandwidth is coming from, is the state stable or not? I think that's the generic answer.
Okay. I think that's all. So thank you very much, Cécile, for your talk, and I see you tomorrow.
Thanks. See you tomorrow.
Bye.